Very good afternoon to everyone. Today we'll be discussing on how the 6G actually affects IoTs. Today we'll be focusing more on drone communications. So let's dive deeper to meet our team today. So our team consists of four people, which is me, Li Tian Yu, Selini Meijia, Ho Ka Heng, and Ko Chuan Jing. First of all, before we dive deep into how does it affects drone, let's take a look what is 6Gs. 6Gs can be summarized into three main points, which is ultra fast speed, AI power networks, and massive device connectivities. It allows connecting speeds up to 1 terabit per second. It also allows like AI driven networks and supports for advanced applications such as XR holograms and autonomous systems. Okay, this is a brief understanding about 6Gs and how can it affect drone. It allows real-time control, high-speed data transfer, massive drone coordination, and edge AI computing. I'll dive deeper into how does it affects here. So this is some of the things that overview that how can 6G actually affects drone over here. In 6G, these are some of the core features that drone communication requires for them to use the 6G features to boost their performance. It allows from area to volumetric spectral and energy efficiencies, quantum security, SON to SSN, 3CLS, and more bits, more spectrums, more reliability. Let's take a look into how does aerial to volumetric spectral and energy leads to volumetric spectral and energy efficiencies. So in the traditional way, which is below 6Gs, it are actually using 2D now. 6G allows it to volumetric, which is 3D to efficiently direct and address this need by optimizing the network resources in three dimensions. These are some of the benefits that it has, like increasing the BPS, increasing the hertz, allowing more connectivity and joules, which is helping in energy efficiencies. Okay, this is how does actually VSC and VEE helps in the drone communications. Let's take a look into VSC. It allows altitude slices, which is that it separates the sky into different layers, which is from 0 to 50 meter, 50 to 100 meter, and 100 to 200 meters. When a drone climbs or descends out of these layers, it hands over to the beam pattern optimized for that altitude. This keep the communication signals throughout throughput high even in dense urban canyons. So like after it's separating them into different slices, which is different layers, the 3D beamforming will make sure that it form narrow pencil beams in three dimensions, which means that drone at different altitudes, even if directly above one another, can each get dedicated capacity without interfering with ground users or other each others. So this is for how does it helps in the volumetric spectral efficiency, making sure that each drone can actually get the optimal performance or optimal signal for it to be working in low latency and high speed. So let's take a look into energy efficiencies. So VEE, it actually helps in smarter power controls. With clear line of sight, the network lowers the transmission power, especially for in flat areas, as it doesn't requires a lot of energy to make sure that it is moving over different kind of dangerous places. But under obstacles, for example, under the bridges or under some kind of concrete areas, the drone systems, the edge computing inside the drone itself will boost powers or use the reflector to prevent retransmission of the signals and make sure that the drone is actually leaving the place as soon as possible. It also directs the power with precise 3D locations. It focuses drones on the energy, hence reducing the ground leakage or cutting joules per downlink beat and lowering the drone's uplink power. There will be lesser handovers over here. So layer cells can reduce the ping pong handovers during the altitude changes and cutting signaling and saving airtime and batteries. So these are some of VSC and VE, and drone can actually help from the 6G core feature itself. So AI-driven orchestrations can help in real-time allocation of 3D beams, spectrums, and power to optimize drone links. It can help in the traffic management of the signal itself. So IRS, which is intelligent reflecting surface, can also help in programmable meta surfaces that can steer or reflect signals into specific 3D volumes to boost the drone's spectral performance. So these are some of the key features on how can AI be used in also the area to volumetric spectral energy efficiencies, which is cloud and edge computing, onboard aware processing, virtual line of sight path, and dedicated area slices, just like what I mentioned already in VSC and VEE. So these are the basic performance that how can drone can be optimized by using the core features of AI. Sorry, not only AI, but 6Gs. I'll pass it on to my partner next. Thank you.
Today's network rely on self-organizing network or SON, which automates tasks like configurations, optimizations, and also self-healings to reduce human interventions. But as we move into the era of 6G and drones, the network must be go beyond just automations. Self-sustaining network or SSN is the next evolutions. This network doesn't just manage themselves, they can learn, they can adapt, and also it can save energy with on-device intelligence, real-life learning, and also energy awareness. SSN enable drones and other devices to make smarter local decisions without relying on the cloud. Well, for the next part, the benefits of SSN. As you can see, SSN can enable real-life on-flight adaptations of communication link to maintain the connectivity despite mobility, interference, and also environmental change. SSN integrates AI-powered energies management in enabling smart decisions like reducing the transmission powers when not needed and optimizing flight path for a better network coverage and energy use. In small or flat operations, the drone can form their own 8-host mesh network. They can sell, use, and reconfigure using SSN principles. Well, in safety IoT system architectures for the drones, first, we are going to have the coverage of communications, computing, controls, localizations, and also sensoring, 3 CLS. In these situations, as we move in the era of 6G, we can know it is important for us to have a true coordinates across the intelligence system for drones. After that, once we have a centimeter level localizations, the device can navigate with extreme precisions. Joint communications and sensoring, JCAS, allow the same signals to carry data and the sense the environments. At onboard and edge computing, we are unlock the real life intelligence where it matters most at the source. And all these enable precise controls. Drone can fly in formations, robot can operate safely amongst humans and vehicles that coordinate without latency. So what is the result? The coverage, intelligence, and the autonomies, the system are not only connected, they are deeply aware, adaptive, and also self-reliant. 3CLS is the engine powering the next wave of innovations, where the digitals and the physics will operate in the perfect sync. So, what is the benefits of 3CLS? Like real life, real time on device making decisions. Edge computing allowed our drones to produce images, videos, and the sensor data and flight analytic on board without relying on cloud. High precision localizations combine GPS and also microwave or terahertz communication signals and the radar based sensorings to send centimeters levels positionings accuracy. Simultaneous communication and also sensorings. Integrated sensorings and communication ISAC enable drones to use the same signals for both data transmissions and also environmental mapping like layouts. Enhance multiple drones collaborations. Our drones can collaborate with each other in order to sharing their data, detecting, and also area scanning. Rather than the raw data, thank you reducing the bandwidth needed to improve the responsiveness. Well, what is the benefits of using 6G in drones? The other way is we can have more beats, more spectrums, and also more reliability. More beats can enable us to have an extreme data rate, while more spectrum that we can apply like we can apply thousands hertz bands. And also, once we have a more reliability, our ultra reliable low latency communication URLLC. In the case of more bits, It will allow us to have a more high resolution video streamings from the drones. The real-life 3D mapping and the environmental scannings, AR and also VR from the drones in remote trainings and inspections scenario. More spectrums by using by using multi-gigabytes wireless link between drones and also ground stations, it will support a simultaneous operations of large drone flights in the dense air space. Allow frequency slicing for task-specific communications like video, telemetry, and also command. If you can, by using 6G, we will have more reliability because we can apply a ultra reliable low latency communications URCCL, mission critical tasks like drone-based medical deliveries, firefightings, and also search and rescue, synchronizing operations for drone swarms, responsive flight controls, and full safe communications in dynamic environments. Well, on the other hand, quantum key distribution QKT for unbreakables encryptions is also important for us by applying 6G on drones. QKT use quantum mechanisms principles to distribute encryption key from any attempts to intercept or use the key alerting both parties. Ensures secure communications between drones and base stations or between drones in swarms, ideal for militaries, law enforcement, or critical infrastructure missions.
Moving on, we'll talk about the system architecture of 6G IoT for drones. First, we'll talk about the core network, central part of the drone communication network, handling data routing, subscriber management, and connecting connection to external network like the internet. Next is the edge computing, performs localized data process and decision making, reducing latency and offloading tasks for the centralized cloud. Next, we'll talk about the radio access network RAN element. Base station, they are envisioned to incorporate massive MIMO NOMA, which is the multi-input, multi-output, non-orthogonal multi-access, which is the middle one of the system architecture. Intelligent reflecting surface IRS, they are used to extend coverage, overcome blockage, and improve signal quality, especially in challenging environment, which is the yellow one, or the below one, the IRS. Next is the drone. Drone has its own edge AI and communicates with an edge server. So the drone will communicate with the edge server nearby him. The interconnectivity. Edge server base station IRS drone user device will have the high level of interconnectivity envisioned for 6G. This support massive connectivity for a vast number of devices. So this is the order of the how the signal trans, transmit to each another from drone to IRS to 6G tower to 6G core and cloud and edge AI. Next, we will talk about the step-by-step data travel across OSI layer. OSI have 7 layers you can see in the screen, and level 7 is the application, presentation, session, transport, network, data link, and physical. And each of the layer have different function. Like application layer is in general the function is what the user sees, how the data is formatted, managing data section, reliable delivery, finding the way, access and framing, actual transmission for the layer 1 physical. So I will talk about the function of each layer and how it works in the drone and also 6G. Application layer. So the source is drones onboard application like for example flight controller, video streaming apps and GPS system. Its function is to collect data and format it into meaningful commands or data stream. For example, a thermal camera on the drone detect a fire zone and trigger an alarm. Next is the presentation layer. Its function is to compress and encrypt the video or sensor data, prepares data for secure transmission across the network. Next is the session layer. The function of the session layer is to establish and maintain communication session between the drone and base station or cloud. Handle session resumption, synchronization, and connection persistence. Next is the transport layer. Transport layer has protocols like likely use lightweight transport like UDP for videos or modified TCP QUIC for control commands. Its function is to segment data into package and ensure reliable delivery. Example is breaks a 1 minute video stream into 10,000 small UDP packet. Next is the network layer. Its function is to assign IP address and route data from drone to receiver using optimized 6G path. Example is data route through a high altitude platform station HAPS to a 6GH server. Next is the data link layer. Its function is to organize bits into frames, add MAC address, perform error detection, correction. Includes handover management if the drone is moving between coverage zones. Important in 6G mobility. Technology use of the intelligent reflecting surface and smart antenna to maintain link quality. The IRS is already present just now to increase the coverage of the drone, coverage of the 6G. Next is the physical layer. Physical layer, the main function is to transmit draw bits over terahertz or millimeter wave frequency. 6G innovation uses advanced MIMO, massive antenna, beam forming, and terahertz channel for extra high speed up to 1 terabytes per second and low latency. For example, video data is modulated, amplified, and sent as electromagnetic wave from drone to nearest access nodes. So just now is the path from drone to cloud. Now is path back from cloud to drone. Is similar, just is similar. So the return signal, for example, 515 left or hover follows the reverse or SI path. HAI cloud generates command is the application layer, wrapped in encryption, presentation layer, session link, section sync, session layer, command split into TCP, UDP segment, transport layer, route via IP, network layer, send in frame data link, data layer, transmitted over 6G radio wave physical layer. So, and lastly, received by the drone and passed up layer to application, meaning that the data is received by the drone and exit the command. Moving on, we will talk about the data voltage across 6G blocks. So this is like a summary from what I've just present, every function of the each layer and the and also focus on the main function of 6G on the right side, which as server use real-time sensor data to adjust flight control. LLM-based AI predicts routing path, reducing latency by 40%. IRS surface enhanced coverage in dense city environment. Terahertz radio enables 1 terabyte per second uplink from drone to aerial base. Next, we'll talk about the classic simplified telecommunication model, which is the 6 blocks, which is the input transducer, transmitter, channel, receiver, output transducer, and destination. Then we will talk about each block function and its use in the 6G drone application. First is the input transducer. It convert physical signals like heat, motion, image into electrical or digital signals. Example in drone, a thermal camera detecting heat, an ultrasonic sensor detecting distance, GPS module detecting location. So the output of this block is electrical digital data. Next is the transmitter. It takes the digital signal and prepare it for transmission. This including encoding, modulation, packet dictation, and amplification. In a 6G drone, data is encrypted and compressed, packaged using a transport protocol, UDP for your modulate using 6G frequency, millimeter wave or terahertz. Same where the drone 6G radio antenna with beam forming or MIMO, multi-input, multi-output. So the output in this block is the electromagnetic wave representing the drone data. The next block is channel. Channel is the medium through which the electromagnetic wave travel. In 6G communication, this includes air as the physical medium, reflecting off building or intelligent surface (RIS), passing through high altitude UAV relays or satellites, experience noise in this block will experience noise and interference or fading. So the output of this block is distorted or delay signal due to noise interference, which must be corrected by the receiver. The next block is the receiver. The receiver captures the electromagnetic signal and reverse the transmitter process. At the ground station or edge cloud server, the antenna receives the signal. The signal is demodulated, and decoded. Error correction is applied. Original data is reconstructed. So the output of this block is accurate and clean digital signal. In this situation, our example is fire location data from the drone. The next block is output transducer. Output transducer transform electrical energy into a usable form such as sound, light, or heat. This happens at the control center, will display the thermal image on the screen or convert GPS coordinates into a map location, may trigger an audible alarm or visual interface. So the output of this block is visual, audio display, or alert, what human interpret. The last block is destination, the end user or system that receive and use the information. In this case, a disaster response officer monitoring fire risk, an AI system logging sensor data and automatically dispatching drones to survey nearby areas, a database achieving real-time drone telemetry. So the final output is to inform decision making or automated drone control response. So this is the summary of the telecommunication model. So first is the input transducer. I said I just present just now. Thermal camera or GPS sensor on the drone. Transmitter, 6G modem in drone, compress, encrypt, modulate, send via antenna. Channel wireless 6G link, terahertz, millimeter wave, I, IRS satellite UAV relays. Next is receiver, ground station, or cloud antenna demodulates and decodes data. Output transducer, computer screen interface, or map display showing fire location. And last block is the destination, human operator or AI system taking action on the received info. So moving onward, we will talk about a real world scenario enabled by 6G drone. So 6G drone can be applied on different sectors. So first is the smart agriculture. Smart agriculture, the drones form mapping soil moisture in real time or watering the plant, fertilizing the plant. So the 6G advantages is the massive IoT support, million of sensor per kilometer square, AI enhanced precision. Next is the emergency disaster response. So drone deployed to search collapsed building. So the 6G advantage is the URLLC, IRS supported indoor signal reflection, real-time cloud mapping. So by using 6G, the drone can give a more accurate, more stable data from to the user. Urban traffic and smart city. Drone managing live city traffic and or crowd control. 6G advantage is high bandwidth data streaming, AI native cloud coordination, which means that the drone will give a maybe more high resolution of video or can give up can can give more drone to monitor to manage to monitoring the live city traffic.
Good afternoon, everyone. As communication engineers working on drone systems, our primary challenge is ensuring UAVs maintain reliable, high-capacity links under dynamic conditions. Central to any wireless link is the battle against noise, which limits communication range, data rate, and link stability, especially when drones are in motion or in harsh environments. Before exploring 6G applications for drum swarms, let's revisit the classical noise sources affecting even the most advanced RF front ends and how we engineer around them. Thermal noise is present in every conductive part of the communication chain, from antenna, feed, and matching network to LNA and mixers. Due to drones' limited payload and power, bulky cooling systems are viable. Instead, we use LNAS with noise figures under 1 dB, designed with high-quality transistors and efficient biasing to perform well at altitude. Digitally, we add forward error correction codes, for example, LDPC and turbo, to correct bit errors from thermal fluctuations, extending range and maintaining data integrity even near the noise floor. Short noise caused by discrete charge carrier movement across junctions affect low current circuits and optimal modules. In drones with LiDAR or cameras, it limits dynamic range. We mitigate it by biasing photodetectors at higher current densities and selecting devices, for example APDS, with quantum efficiencies above 80%, improving photon to electron conversion and also reducing noise relative to signal. Flicker noise from charge trapping in semiconductors and resistors impacts low-frequency analog and RF front ends, affecting control and telemetry links. We countered this using chopper stabilization, auto-zeroing, modulating signals for amplification and demodulating back to cancel flicker. Any residual noise is removed via digital high-pass filters after ADC, preserving control loop precision even in variable signal environments. As we as we move towards 6G using terahertz spectrum, new noise sources appear, notably molecular absorption noise at 300 GHz to 1 THz. Water vapor and gases absorb and re-emit energy especially in humid conditions. This raises attenuation and the noise floor. We mitigate it using adaptive frequency selection. Drones scan for transparency windows with minimal absorption. Swarms dynamically coordinate subbands based on onboard humidity and pressure sensors. 6G also favors dense, small cell topologies even in 3D space, using airborne relays or tether stations to reduce link distances and mitigate path loss. Another 6G challenge is interbeam interference in massive MIMO arrays. Drones use beamforming to direct narrow beams to ground or other UAVs, but misalignment or side lobe overlap can cause interference, degrading throughput and stability. We use zero forcing (ZF) beamforming to steal news and unintended receivers, eliminating interference where arrays have sufficient degrees of freedom. Where CSI is imperfect, we shift to MMSE beamforming, balancing interference suppression and noise amplification. On-board FPGAs or AI accelerators compute beamforming weights in real time even during fast motion. Layered over this is AI. Now central is channel estimation, modulation, and beam steering. In swarms, AI models predict optimal beam directions and coding rates as drone move. However, AI introduces its own noise through prediction and adaptation errors, especially when training data lacks rare conditions like obstacles or sudden weather shifts. These lead to suboptimal decisions and higher error rates when reliability is most needed. To reduce AI-induced errors, we developed robust training pipelines. Offline training injects synthetic impairments, Doppler shifts, hardware non-linearities, and also various weather conditions. We also apply adversarial training to build model resilience. In the field, real-time learning updates model weights using live SNR, packet error, and alignment metrics, often via reinforcement learning. If confidence drops, we fall back to classical estimators and conservative modulation schemes. Uncertainty qualification, for example, Monte Carlo dropout, gives confidence bounds, allowing adaptive fallback to safer modes when predictions are unreliable. Bringing all this together, RF design, R6G radio strategies, and also resilient AI is key to unlocking drone swarms potential. Imagine a post-disaster search mission. Drones stream HD video, LiDAR, and infrared data while coordinating autonomously. Thermal or flicker noise could disrupt telemetry, molecular absorption could cripple video links, beam interference might jam signals, and also AI mispredictions could spike error rates. Only by combining cryogenically optimized LNAs, efficient photodetectors, tropple stabilization, adaptive spectrum use, airborne relays, ZF or MMSE beamforming, and robust AI pipelines can we ensure resilient communication under extreme conditions. Engineering robust 6G drone links is a multi-layered task. We start by mitigating classical noise, for example, thermal, shock, and flicker, through smart hardware and signal processing. We then address 6G specific challenges, for example, molecular absorption, beam interference through adaptive frequency use, dense topologies, and advanced beamforming. Finally, we integrate AI for real-time adaptation and resilience. By tackling noise across device, signal, and algorithmic levels, we build drone swarms with ultra-reliable, high-throughput links enabling future missions in disaster relief, precision agriculture, and beyond. 6G will be the backbone of tomorrow's autonomous, intelligent drone networks. Now, let's look ahead. The, the fusion of 6G, IoT, and drone technology opens doors to innovations we once only imagined. With holographic communications, we move beyond screens into real time 3D interactions that feel almost physical. Drone swarms will operate as intelligent, coordinated fleets ideal for deliveries, search and rescue missions, and environmental monitoring, all with zero human control. And with fully autonomous systems, drones and IoT devices will think, respond, and act on their own, revolutionizing everything from smart cities to industrial automation. These aren't distant dreams, they are fast approaching realities powered by 6G. To wrap it up, 6G changes the game entirely. It's not just about faster speeds, it's about smarter, seamless communication. It completely redefines how drones operate, enabling real time collaboration and autonomy. It transforms IoT ecosystems, making them more responsive, efficient, and intelligent. And most importantly, it unifies everything. One powerful platform for devices, drones, and data to work together in harmony. This isn't just the next step. 6G is the revolution that's shaping the future of communication. Thank you.